So we've been looking at parametric and non-parametric methods. So let's just have a quick recap of what we've been doing here. So we've got, when we've got two groups, which could be paired or unpaired, we have t-tests for our parametric methods, which are the ones that we mainly use. And we also have seen that we have these Wilcoxon and Mann-Whitney tests as a non-parametric equivalent. They work on the ranks of the data rather than the actual data. For multiple comparisons, we have the ANOVA test for the parametric model, and we have the Kruskal-Wallis test for the non-parametric model. Then when we want to go on to pairwise comparisons, we can see that we have the pairwise t-test, we have the pairwise Wilcox test. All of these things all work with a p-value decision rule of 0.05. The only thing to note there is there's no variance ratio test when we have, there's no formula selection for the Kruskal-Wallis or the two-sample test, so we don't have any variance ratio type tests or Bartlett tests sitting in there. But basically we can see that for every test that we want to do, we have the non-parametric equivalent. So we've been talking a little bit about fish stock, so I guess it's worthwhile placing some of this in some actual context. So that's what I'm going to do now. Pretty much what have we seen happening? We've seen really depleted fish stocks globally. This has happened for a number of reasons. We've seen, a greater effort, a greater fishing effort. So that means, in effect, more boats in the water. We've seen radical increases in the technology we can use to catch fish. Not only have we seen changes in technology, but the ability to stay at sea longer. So if you can stay at sea longer, that gives you, greater effective fishing effort. And so all of these things have led to declining fish stocks. So if we plot this, and in terms of the curves that we've been looking at, so exponential decay was the shape of the curve that we looked at in pollution, and you can see here that this is the same pattern that we get here. What I've got on the vertical is, a measure of catch standardized by the number of boats, and not just the number of boats, it's sort of the effective fishing effort. And you can see that as we've put more, we are still actually taking, large amounts of biomass out of the sea, but the amount of fishing effort that we're putting in to take that biomass has radically increased. So we've had this exponential decay, and this is across a wide range of fisheries. So many, many more boats in the water to take either the same amount of catch or falling rates of catch. Right, so that's a general representative overview of what's happening in the fisheries space. Why do we overfish? So it's deemed as this idea of the tragedy of the commons, which is an idea that's been around for a long idea. Some people may have taken environmental economics. I think this might be a topic that they cover in that course. So we're just making ourselves aware of this, and the way that this sort of tragedy of the commons idea plays out in the fisheries space is the logic that I've mapped out there in those 5 steps. So everyone is competing for the same resource. If you do the right thing, then there's no guarantee anyone else will do the right thing. So if you fish responsibly, you're leaving fish stocks for others to fish, and you have no control over that. And so you think that they're going to take those fish. Nothing is stopping you. So this leads to the unstoppable logic that you may as well overfish as well. So there's nothing stopping other people exploiting the resource. So we have this race from everyone to exploit the resource first. And this plays out time and time again. So we have a common property problem. So no one owns the global oceans. No one can put any control on them. So if you don't catch the fish, somebody else will. So you may as well take as much fish as you can today. And that's what drives, there's a little bit more to it, but that's basically what drives the tragedy of the commons problem. The extent, how widespread is this? So it's not just something that we see happening in open oceans. Okay, so that's something to bear in mind here. The problem, we're getting better at fisheries management, but there are still fisheries that are close enough where we have catch limits being set and they're being set too high, and we see fisheries collapse. Famous example of this is the Grand Banks fishery. So this is a cod fishery off Canada, and I'm just showing you, where it is. And if you look at the amount of biomass that we took out of this fishery, so I've gone and collected some back data from this, you can see that we're going along, taking out taking out a large amount, like this is a large amount of fish stocks, have a bit of a dip, then this big escalation, and then collapse. So that's our story for the Grand Banks. And this fishery has essentially collapsed. The biomass has been depleted to the point where, despite closing the fishery, we have not seen the fish come back. So this is a fishery that was not the open oceans, and things still went wrong. So I think it's important for us to understand this, to look at what possible things can go wrong, and not to think that, oh gee, we can have smart scientific fisheries managers here. We can always solve this. So what went wrong in this fishery? So there are a number of things that went wrong here. So we had a technology interaction. So there was a way that the fish sort of, would disappear from different areas every year, and we could still find them. Now, as technology, the ability to find them improved, that wasn't picked up so much. So the reason that we were finding them, we're still finding the fish, was because we were getting better at it, and that wasn't picked up in the way that we were measuring things. So there was a technology interaction that people weren't really aware of, and that can be something that we always need to be aware of. We have random shocks. So we build these models, but there is some inherent uncertainty in the models. Not only is there inherent uncertainty in the models, you can have these dramatic external events. So if you deplete the biomass, you could put it at risk of a negative shock. So for example, some tornado or some system that comes through really disrupts the recruitment of biomass for that year, and then we've got a problem. Okay, so if we get these shocks coming into the system, that can really stretch things around. And of course, our old friend here, there were vested interests, and there were, the scientists in some settings would provide some information, and the political pressure and the fact that livelihoods were at stake, jobs were at stake, meant that biomass limits were set too high. So that's something that's still at play today. We see that in a lot of fisheries around the world. Even when the scientific evidence is being provided, that interaction between the political, business, employment, people's livelihoods, plays out in such a way that the limits that we set are non-sustainable. So if we just look at this, if we go back to Grand Banks, what we have is what I've got here is what we do a little bit of now is, reconstructed estimates of the fish stocks. So what I've got here is some estimates that are provided from, scientific organizations of how we thought things were traveling. So this is some of the spawning biomass. And this is what it turns out was true. So, after we've seen the system collapse, after we've gone back and historically worked out, gee, how did the system collapse? This is what people have backcast as for truth. And yet at the time, people thought it was much higher. So, your models can be wrong. Here's an example where there are a whole range of things that were interacting. So we thought, we thought we were doing some reasonable management on this. We had all those other pressures going on. Gee, we got it wrong. And you can see that the spawning biomass collapsed through time. So that was the story of the Grand Banks. It's a combination of not just unregulated tragedy of the commons type problems. It's a problem of scientific uncertainty, commercial interests, and a whole range of other things at play. So what's going on really in the space? If we're depleting these wild fish stocks, what do we see? We have seen a rise in aquaculture. So we're seeing lots of interesting things in the aquaculture space here. For example, fly and maggot meal products to try and include in fish meal rather than using other lower levels down the trophic food chain for fish meal. But you can see here that what we've got here is our global amount of protein, I guess, really coming from fish. And you can see while that's what's happened is there's our wild caught and there's aquaculture. And you can see some examples, China has been an area where this is exploded. And we see a lot of this in other parts of Asia as well. Vietnam is a large supplier of aquaculture product, and Indonesia is actually a particularly large supplier of shrimp into global markets. So around our region, we do see a lot of aquaculture type production coming into play, and that's got its own problems if we're clearing mangroves and other areas for this kind of production. But that's sort of the rising potential for replacement of product that is being depleted. We're looking towards alternatives to supply that protein. So we get a reasonable amount of protein in our diet globally from fish. So if we lost that, that would be a significant challenge for us to deal with. So if we take that on board and now think about some of the kinds of questions that we might frame as interested in research, or that might draw on our statistical analysis kinds of techniques that we might think about, we can imagine one context might be to develop some new strain of fish for the aquaculture options. Here I've picked a strain of tilapia. This is a fish type that is not, there are some potential issues here, but it's something that eats pretty much anything. So we don't have to worry about too much about, if we're generating protein from tilapia, about it depleting other sources of protein, as we do for things like salmon. So when we farm salmon, we use a lot of other fish to produce 1 kilo of salmon. We use several times that amount of fish product. So we are taking things lower down the food chain to feed to our salmon. So some people have argued that just because it's fish farming, it's not necessarily sustainable. So we're looking for things that might be able to be farmed where we can supply the feed to them without putting additional pressure on fish stocks. Now, the idea, of course, if we want someone to take this up, well, it's going to have to be a profitable business. We have to accept that the only way that we can get this to be, taken on board would be for it to be profitable. So we need to be able to grow the best strains. And that's some of the applied research that people do. How can we select the best strains? So we've got an experiment, so we don't have those problems of going out and getting, rare and unusual data. We're going to be breeding these different strains of fish, so we can think that we can use some parametric methods to investigate our question. And probably we're going to have multiple strains. So here I've got 3 potential strains. So if we've got 3 potential strains, we've got, reasonable sample sizes. What does that mean? It means that it's going to be an ANOVA test to try and identify the best strain for production. So what would be our steps for progressing this? Well, just like we've seen in other contexts, we would have our experiment running. The data comes in for us to analyze. We're going to create a box plot so we can get a visual understanding of it. We know that when we flip back to the parametric methods, we have one formula if the variances of each group are the same, another formula if the variances are different. So we know that we're going to have a Bartlett test, we're going to conduct the ANOVA, and then if we detect at least one difference, that is, reject the null for the ANOVA test, we're going to go on and conduct some multiple comparisons. All right, so what would we do? We would get the data into R and then have a look at it. So you can see that the way that I've got my data sitting in here, read in my data file. I use the 2 commands that I most usually look to have a look at my data are the head command and the structure. I like the structure one because it tells me what I've got. It says I've got a variable weight and I've got a variable strain. Strain is a factor variable. It's got 3 levels there, the words that I've got in here, and you can see here this is my strain A. So when I have the head, I can see the weight measurements of my fish. These are, at a certain growing time. For example, it means that, after 30 days would be a harvest date. So I've harvested them all at the same time. And that we would need something, our production system might be set up so that, for our ponds, we have bacterial buildup after 30 days, say. So after 30 days, I need to harvest my fish. So we harvest the fish, we weigh them all. We want to see which one looks better. So let's have a look at our plot. So we've decided that all of these strains harvest, all of the ponds stocked at the same time. Then we've emptied all of the ponds at the same time. Got the same number of observations in each group. And you can see here, I've got 3 levels of here. I've got 86 observations in total, 3 levels. So I've got a nice sample for each of my groups. I've plotted them all out. All right. And so this is my weight after 30 days of growing out in my ponds. I've got quite good growth. And you can see that we do actually see some differences visually. You can see that the strain B looks like it's a little bit higher. But the question we want to ask is, could the differences that we observe be due just to sampling variation? Okay, so we know that that samples from the same population will vary a little bit due to sampling variation. Okay, so we know that if they just look a little bit different, that's not evidence that they truly are different, or we don't have evidence that they're truly different. So we're going to set up our formal test. I also look at these and I say that the shapes are pretty similar. So when I conduct my Bartlett test, I'm looking at the shape and I'm thinking my null hypothesis is that at least one of the group variances is different. I don't see any strong evidence that the group variances are different in these plots. So let's have a look. So what do? I conduct my Bartlett test, and you can see here, Bartlett test, weight, tilde, strain. So I've got 3 groups in there. They're my numerical values, and I get a p-value of 0.78. So that is, do not reject the null of equal group variance. So I'm going to go on now and conduct my ANOVA test. My ANOVA test is going to try and detect at least one difference. So let's go on and conduct our ANOVA test. So if we look at our ANOVA test, what's our null? All the group means are the same. At least one is different. How do I conduct the test? One-way test, weight, strain, variance is equal to true. So that gives me the formula that I want to see. And you can see that I get a p-value that is less than 0.05. So that means that I am capable of rejecting the null that all the group means are the same. So at least one of them is different. Now I'm going to go on to multiple comparisons. So the thing I want to understand with my multiple comparisons is a neat way to express all of the possible null and alternate hypotheses that we're going to test. So that's what I'm going to look at now. So rather than using just one, like writing them all out, all the possible comparisons we do, we use this language here. So we've got a little bit of experience using notation. So we say the mean of group I is equal to the mean of group J for I not equal to J. And the alternate is just not equal. So what does it mean? Group I is A and J is all of indexing the groups again, but it can't be A. So it's A to, so this says compare A to B, A to C, and B to C. All right, so with just 2 lines, I can write all of my null and alternates. I can have them all covered. And the advantage of that is that you can see if we had 4 groups, we would have 6 comparisons. So we can radically reduce 6 groups to just two statements. We then go on to our pairwise t-test. Again, because our Bartlett test, we did not reject the null of equal group variance. We use this pooled standard deviation in this test, and then we get the comparison. So we see that where does the difference come out? The difference is between A and B. And we see between C and B and A and C, there are no differences. So that would be an example where we have worked through using our ANOVA test, something that has built up based on, a real world context. We see the fish stocks being depleted. We want to do something about it, so we want to get into the aquaculture space. If we're going to get into the aquaculture space, we have to acknowledge that it has to be profitable if someone's going to take it on. For it to be profitable, we need to be growing the largest strain. So we've identified the strain that's likely to be something for us to focus on. And that's a reasonable opportunity for us to pause.